I want to just give a quick overview of what my thoughts are with Dr. Marchetti. I think really the beauty of the DMT test is its measurements are just extremely sensitive to soil behavior. And what's really nice about it is it's correlated with properties and that we commonly use. We're already familiar with them. Phi angle, SU values, K naught, stiffness values, the M value, pre-consolidation pressure, all things that we're commonly familiar with. So it gives you excellent correlations with them. And what Dr. Marchetti did that was so wonderful, really, is his research was so well done that in his 1980 paper, we're still using the equations that were presented then. So, I mean, that's really, really spectacular. And we also have the real nice thing later on this afternoon. He and his son Diego have worked on the seismic dilatometer, and they've got it now, so it just uses one cable, and it uses a true interval seismic. The geophones are half a meter apart, so one hit and you get both readings and you get to see them, and it gets shifted on the computer, and it's just unbelievable. I worked with them on Friday, and it was just spectacular. So without any more waste of time, just have Dr. Marchetti come start his presentation. Let's congratulate Dr. Marchetti.
Well, thank you, Roger, for your kind introduction. I want to thank all the people who have made this conference possible. First of all, I think Roger Feldmetzger, and then John Carlton. And I also wish to thank Professor Schmertman, Yamilkowski, and Maugeri, who, with their contributions and presence, have given light to this conference. I also wish to thank my colleague Monaco of L'Aquila University, which will share with me the pleasure of this presentation. Next one. No, previous one. As you can see from the title, the previous one. As you can see from the title, we have both DMT and SDMT. Since I have been asked to give a course, I have to apologize with many people which already are familiar with the basics, but since maybe some participants are not familiar, I thought I had to start again, of course, quickly. In essence, what I'm saying that is the initial part of this presentation will be maybe repetitive for some of you. The more spicy part will be the second part of the presentation, because we shall alternate with each other, 4 people, and so you will see changing faces. So as I announced, we are now starting with the mechanical DMT, and later we shall talk about the seismic DMT after the break. The summary, what we are going to see is I will mention what is the available documentation. But let me see immediately that probably the most important reference is the TIC16 report, which was done in 2001, and more or less summarizes 95% of what was scattered in many papers. So if anybody is interested in many more details that we are talking here about, this is the proper reference. This reference is reprinted in the book you have received, so is very easily available. We shall briefly describe again the equipment, the mechanical equipment, the derivation of geotechnical parameters. This is an important point because, as Roger already said, we like to go from DMT results to soil parameters, not go directly to bearing capacity or these kind of things. We want to go to parameters that you can also measure in a different way. So before deciding the design profile, you may have a critical view of all parameters obtained in different ways, and if you like, you select what you want. Then we shall talk about the specific of some applications, in particular settlements, which is probably the application number one of this tool. The coefficient of consolidation permeability to verify if a slope contains slip surfaces, laterally loaded piles, which is the original reason why this instrument was conceived. We shall talk about the liquefiability of sands. I think we have today very quite heavy contribution now on liquefiability, and this will be presented by my colleague Monaco and by Professor Maugeri tomorrow afternoon. There is a paper on the proceedings which is more or less a state of the art of what we know today about evaluating liquefiability of sands by DMT. A few words about compaction control, about pavement subgrade modulus to check the compaction of the pavements, of the subgrade underpayments. Something about the springs for diaphragm walls, because of course when you have to design diaphragm walls, you would like to know what the springs you have to use, and this is a contribution in this direction. And then we shall say a few words about how DMT, if and how DMT can help for selecting finite element input parameters. Key references, I think most of you already know, but the standards, the important standards are the Eurocode 7 and the recent, relatively recent 2001 ASTM standard. As manuals, I remember the first manual that we made in Gainesville with David Krabs, and that was 81, which is now absorbed by the later manuals. Also, Dr. Schmertman made a very heavy contribution in 4 volumes, which of course are not easy to have available, but are a good, very good source. But much of the material of all these manuals has been transplanted into the T616 report. The last 3 with the arrow here are perhaps what we still have to use today. Maybe the last 2 in particular. All of them are anyway in this bibliographic site that I started 3 or 4 years ago, and from which you can download almost anything, in particular these 3, and in particular these 2, because I think this is really the one that is a basic reference. But if you want to have details on instrumental details, you can go here. This is like a manual containing many details on the mechanics of the instrument, but we don't want to go into these details this morning. But you might be if you're a user, this can be quite helpful. As most of us know, the layout of the DMT is the one which is indicated here. We push, sometimes drive, but it's not recommended to drive. So we push the blade, we stop at the given depth, then we inflate using the control box, inflate the membrane, and for some time nothing happens because first you have to counterbalance the pressure applied by the soil. And when the 2 things are equal, the membrane lifts and the contact is no longer a contact, and so you take the pressure this time, then you inflate and you take the reading, the pressure reading when you have inflated 1.1 millimeter. Maybe I can tell you the story of the 1.1, but anyway, this is the way it is today. The push force can be provided by most efficiently by a penetrometer or by a drill rig, which however are not so effective, or almost any other equipment, because the test is not pushing the soil, pushing the instrument, but the dilatation of the membrane. So you can more or less install with every possible method. As I said, the most effective way is using a penetrometer, possibly a 20 tons penetrometer, and in which case, however, it's better to have stronger rods than the typical 36 millimeter rods, because otherwise you have 20 tons, but you have to stop because you are in danger of losing your instrument. So I have seen many people having a 20 tons truck and then they stop because of the rods. So we prefer to use 43 millimeters rods, very strong. So we can apply all of the 20 tons. Otherwise, you can use the pull down, the push force of a drill rig. And what we also like very much is sometimes, this is what we prefer, of course, but when we have drill rig, we use the torpedo configuration, in which the idea is to avoid threading the cable all the way in the drill string, but only in the last, say, typically 3 meters. Then the cable exits laterally and goes up in the annular space between the rods and the casing. Here you have some picture. It's important to have a collar, a slotted collar in which the cable can go through, so it can be protected in case there is some contact with the casing. As you can see, well, this is actually is a 6 meters torpedo. As I said, can be typically 3 meters, but in this case it was 6 meters. And then the cable exits laterally here. So you pre-assemble the thing before. It's like an SPT, and you attach it at the bottom of at the end of the drilling rods, which of course are more robust than the torpedo, because the torpedo typically is 36 or 50 millimeter diameter. The drill rods are typically 3 inches. So buckling is less of danger. Of course, by this method, you get every time only 3 meters of a stretch of 3 meters of profile. Then you have to clean the hole, to extract the tool, to clean the hole, to advance in the penetrated soil, and to start again from the bottom of the borehole in the virgin soil to make an additional 3 meters of testing. This particular necessity in when you are at sea, because for the reason I just said, that you can push on the drill rods, which are rather robust, and this can avoid buckling, but then all the force go to the torpedo, which is smaller in diameter. The soils that can be tested by DMT practically are all the penetrable soils. Often the limitation is not the DMT itself, but it's the push capacity, because the blade itself is very, very strong, can withstand more than the capacity of common trucks. Since the method of measuring is the balance of zero, we can, the resolution is quite high and depends on the resolution of the pressure gauges, really. So we can get results also in even in nearly liquid soils, which means that in clays, CU values can go from nearly liquid material to nearly MR, and the moduli up to this value here, indicated here. Of course, gravel is not welcome. Sometimes if the gravel does not tear the membrane, you can cross half a meter, even 1 meter of gravel, of course without taking readings, because readings have a significance only if the soil particles are a small fraction of the diameter of the membrane. Most of you probably are familiar with this picture illustrating the working principle. I don't want to go into details. I just want to say that everything here is mechanical, so the operator cannot calibrate or adjust anything. He cannot make any damage or personal touch. there is no way that it cannot get 1.1 millimeter. So, as I said, the dimensions are fixed. 1.1 is the difference between the height of this quartz cylinder today and this sensing disk. The difference is exactly 1.10 millimeter. So the extension, the movement of the membrane is very well defined. This is important because what you have to verify from the verification viewpoint, so when you need to verify or to make quality controls, you just need to verify the pressure measurement, because the only measurement is pressure. There is no way of you can get out of calibration for the settlement, for the deformation of the membrane. You see, often, I don't know in this country, but in our country very often bureaucracy requires when you use pressure gauges that you send them to universities to calibrate, which is a very ritual situation. In our case, since we have two gauges, one checks the other, and this is a sufficient check. We never had the problems with the two gauges. So if the second reading is within a few percent from the first reading, you are right, and in my opinion, the calibration that might be asked by the bureaucracy are superfluous. What really counts is the accuracy near the zero, and not really the accuracy, because if even some nonlinearity is not important at all. What is important is the resolution and the repeatability, not the accuracy. But all these are already built in, because as you see, the initial part of this gauge is exploded here, so the reproducibility and the resolution are very high. So many of the problems behind this are not seen by the operator, by anybody, because really do not exist. So the calibration can be done, but I think it's just for bureaucratic reasons. Reproducibility of the MT is, everybody who has done a DMT knows that is very reproducible. Even more than reproducible, I would say independent from operator. One of the things I have always disliked since the beginning of my career was when I got results from some in-situ test I don't want to mention. And people told me, but these are made in a country in which they are not so accurate. So if it is a moving target, no good. So I think in the operator, every operator should get the same results. Here are 4 people alternating doing this test, and you can see that the results are the same. Also, I want to show that to point out that these are not this is not scatter, because it repeats. So you can see. Sometimes I've seen people when they see, for instance, in Venice, in which the soil is very much layered, they see this is scatter. It's not scatter, because when the soil is linear, the results are very linear. In the T16, there is a collection of the 9080 formula, so you can have this table. And well, first of all, we call A and B the two readings that you get, or P0, P1, when they are corrected. So sometimes in my talking I use A, B, sometimes P0, P1. Really, P0, P1 are the corrected A and B readings. And the correction is due to the fact that the membrane has some rigidity. Ideally, the membrane should have no rigidity. In this case, they would be the same. But since it has some rigidity, you have to make a correction. But basically, apart the correction, A is P0 and B is P1. So these are the two corrected readings. From here, you go to here, which are intermediate parameters. in which a parameter is the material index, telling you what if the soil is silty, clay, or whatever. Then KD is like an amplified K naught. KD would be K naught if the soil was not, the stress was not amplified by the penetration of the blade, because the wedge of the blade, of course, increased the horizontal stress. In fact, in normally consolidated clays, for instance, in which K naught is about 0.5, we have a KD equal to 2, 4 times more. So KD can be regarded as an amplified K naught. ED is obtained as from theory of elasticity, so is the modulus in which you have a formula, elasticity formula from the deformation of the membrane and the pressure. And so I think many of these formulas should consider not empirical. I don't like empirical in the sense that you try to correlate anything to anything. This is not good, I think. But I like when with most of you know from your theory, you go up to the last point that you can. And then maybe if something is missing, you just make a correction. For instance, if you had the volume of the sphere, and you have to have a formula in which you know that the volume is proportional to the cubic d, then if the theory is not available, you empirically, maybe you can correlate the two things. But you have always to try to make correlations between the things, properties which are physically well connected. For instance, M, we don't use ED directly, we use M, because there is a correction factor. You see, you don't use ED, but you have to correct by RM, and RM has a lot of responsibility. He has to convert ED for many things, for the distortion caused by the penetration, horizontal to vertical, because of course we are loading the soil horizontally. Generally, for everyday applications, you want the vertical modulus. And then let's not forget that in clay, of course, we are in undrained conditions, and we want a drained parameter. And of course, the link is through, say, the Skempton parameter A and B, which depend on soil type and stress history. But since you have ID and KD, which is stress history, you can hope there can be a correction that give you usable M. And in fact, this is, has been checked, because this is just the reason behind why you can attempt correlations once you have some good expectation that the correlation can work. This is the way that after many years we think is the more expressive way of presenting the results. Here you see the material index, you see here clay, you see here sand. Then you have the constrained modulus, which here in sand is, in this case, is much higher, and very often is higher than in soft clay. You have the shear strength, Cu, then the shear strength. Of course, you don't have the shear strength where the ID tells you that you are in sand. Then you have the horizontal stress index, which is one of the parameters I look first, because he tells me the history of the deposit. So though KD, which is correlated to OCR, is not used directly in normal foundation, for instance, calculation. However, OCR, we know, dominates soil behavior. So since KD is very similar to OCR, this parameter gives you a look of the stress history. Some people prefer to display these results in this way, which is only P0 and P1. I strongly dislike this way of presenting the results, because the reason why they present it this way, because they say this is objective. So it's true, this is objective, this has interpretation, but this is completely incomprehensible for anybody. Like if you gave the results of the dilatometer without showing the curve. They would be more objective, but inexpressive. I think a proper way is to show in this way, maybe even adding P0, P1 if you want, and of course stating the method by which you have interpreted P0, P1. How to use the results? MSU we use in the common usual way. ID soil type is nice to know if the material is sand, silt, or clay. Though this is a nice extra, it's not, the tool was not done for for this. As I said, KD has a similar shape of OCR, and it's important for some applications that we shall talk later to keep in mind that KD equal to means approximately OCR equal to 1. I show very briefly some comparison between predicted strength and predicted by other methods. In other words, calibration of the DMT prediction in places, national sites in which already these parameters had been measured before. Well, actually, this collection of OCR results made about 15 years after the initial 1980 correlation by some Japanese, and they found, collecting all the available OCR, a line which practically was coincident with the previous line. So what this slide tells us is that subsequent research has found that the initial correlations were essentially adequate. This has some interest because it's comparison between the curve that we have just seen in the previous slide, obtained by calibrations, OCR, KD. But here we have a theoretical prediction made by Finno, quite some time ago, by a strain path method and the isotropic bounding space model, which is a model I don't know if you are familiar. I'm not particularly familiar with that. Anyway, he found these bars here as from his theoretical study. So this is a case in which, again, sometimes the calibration is the most expeditious way when the mathematics is not ready, provided, of course, the physical link is there. So this is a confirmation by theory of something that was calibrated in absence of the theory before. These are CU by DMT, which is the continuous line. These are CU by, let's say, high-quality triaxial sample, because this was Kisojiban, which is one of the biggest firms in Japan. And frankly, my opinion is that if there is this scatter, this is the scatter of the triaxial, not of the soil. But anyway, the general agreement you can see is correct. This was in the first international conference, so that was more than 20 years ago, and somebody showed the prediction of CU by field vein, which are the dots, and the prediction of CU by Dilatometer in Canada, and they agree well. Next. Here we see the comparison at the national British site about Kenner, and we see that the CU by DMT fits in the middle of other results. And here is, for us, is a very much studied national site in Italy, this Fucino clay, because there have been various studies by many international groups. And again, you see that the DMT, which is the black line, is in the middle of other results. Of course, with CPT, you can also have a very good result, but the trick is you have to have the proper value of the denominator. Maybe I have not mentioned, but all these black lines representing DMT have always been interpreted in this context by using the 1980 correlations. So there is no adjustments or corrections, always with the 90-80 correlations, which give you just one value of CU. Next. When you want to check things, you have to go to different places. So these are results in other places between vein and CU, and again the agreement is good. And here is our friend Roberto Coutinho, who did this test in one of his research sites. And again, DMT is in agreement with other results he got. So the conclusion on the accuracy of CU is, and many others indicated that generally CU fits, is okay for everyday practice, works in many geographical areas. Of course, a purist could say that we know that CU is not unique because we have triaxial compression, we have extension, we have simple shear, we have place strain, field vein. But how many of us use more than one CU in everyday design? So we think that having already a reasonably accurate CU value is already something. Now we go to, until now we have seen CU. Now we are seeing the odometer modulus, and again we see a good agreement between odometers made at the Norwegian Geotechnical Institute and this band, which is the dilatometer. And again, I think this scatter is more the laboratory or the sampling than the soil. This agreement by the same people that the Kiso-Giban firm. These are the results in another clay. Now, so what we think is the application, the most useful DMT application is the settlement. And what we recommend is the one-dimensional, or what we use at least, is the one-dimensional method in which you have M given by DMT. So you have no choice if you use this method. And the delta sigma V by Businesq. Again, you have no choice because Businesq is Businesq. And this is the formula, the one-dimensional Terzaghi formula. If you really want, you can use, of course, the three-dimensional formula, the Hooke's law. There is a relation, as you know, between Young's modulus and constrained modulus, which from Poisson ratio typical values gives about this relation, 0.8. But you get similar predictions because this is lower, but then you have to detract something. So this formula and this formula are nearly equivalent so far as the quantity you obtain. But the point is this formula is simpler, not just for simplicity, because you cannot play games with the results. Here you can have a different Poisson ratio. You can have this conversion with different Poisson ratio. We also know that the horizontal stresses are not so well predicted by Businesq. So I think this formula is nice because the settlement you get, this is the important thing, is independent not only from the operator but only from engineer. Because the engineer, if he uses the results in a bad way, can do as much damage as the operator. In this case, there is a unique path from the soil to the settlements, and nobody can obtain a different settlements because there is no way of playing games with the results. One note, this settlement does not include secondary. As was stressed in many previous documents, MDMT just for primary, because of course during the test you have no time for secondary. And so MDMT must be treated as if it was obtained by odometer. Now a question can be, it is legitimate to use M constant in the settlement analysis because as we know, M is a variable, is not a constant during loading. M is defined here, is 1 over V, but is at the vertical of overburden stress. And we know that if we have a sharp break and we are exceeding PC, M has a sharp drop and then starts again. So can we really use a constant value of M? Well, this situation with a very sharp break is generally so sharp in some structured clay, some Scandinavian clays, but in many clays may not be so so sharp. So if, and probably even in most sands, there is no such break. So the transition is more gradual. So in many cases, this break is not so marked, and the transition is more gradual. And in practice, we can use M in many cases. As was in the previous slide that I remark, Poulos clearly in Istanbul said something we all know, that what is important is not the formula, but the modulus. So if the modulus has a, what is important is to have a modulus which is not 3 or 4 times wrong. This is important. The rest is, the formula is not so important. And even this accepting that this can be considered a constant is not so terrible compared with errors that you can do in by different methods. Already in '86, Schmertmann had collected a number of cases, predicted versus observed settlements, and obtained a ratio of calculated versus observed very near to unity. So this was an early indication of the adequacy of using MDMT to obtain settlements. Next, please. This was a subsequent collection of results by Dr. Hayes. Should be the 45 lines, is not, but is very acceptable. I don't show, of course, case histories here because there is, for many reasons, we have no time, but there is a specific paper in this conference that has collected quite a large number of predicted versus observed settlements, a review of the available experience by Monaco and other people of our group. So if you are interested in comparison between predicted and observed settlement, you can go to this paper in the book of this conference. We might wonder why we presume that DMT is, it appears that the DMT is better in getting settlement rather than other tools. Well, Yamelkowski, as far as the ratio Young's modulus over QC is concerned, found the calibration chamber quite a high variability between 2 and 25. And this was a function of OCR. But of course, the question is who will give us OCR? Because if we just have QC, we cannot use at the same time QC to infer OCR. So this is a quite a large range. Probably in practice, this range is a little smaller, but anyway, it's quite a very large range. Schmerten initially suggested a value of this ratio of 1.5 to 2.5. Fay told me that in their stiff sands in Perth they use a ratio of 13, and Antonio, maybe he can confirm, told me if he uses a ratio of 4. So you can see that if you are trying to obtain modulus from CPT, the key is in selecting a proper value of this ratio that can vary in a relatively wide range. Here the bandwidth of maximum to minimum prediction, these are settlement really, are not moduli, but anyway, is the same thing, is much narrower. This is another slide presented by two persons which are in this room, by Bullock and Metzger, and they showed again the predictions made by SPT and made by DMT, and measured versus predicted. You can see a much larger dispersion by SPT than by DMT. Sometimes people say, but there is a lot of experience with SPT, but even if you have a billion measurement, this is not going to reduce the variability. Possible reason of the higher accuracy of DMT, we think, are first of all, in my opinion, the availability of the stress history parameter, KD, which is connected to OCR. Stress history is very important to control settlements. Then, of course, a wedge deformed the soil less than rupture test. And then the modulus by a mini load test relates better to modulus than a penetration resistance, because actually what the DMT does is like a lateral embankment against the soil. So this is more similar to a modulus than the penetration resistance. Another piece of information that, in my opinion, solidifies the reason, supports the use of DMT for as operative modulus, is that it is very similar to what the textbook recommend. If you go to foundation engineering handbooks, you find that for various types of soils, they give you these values, they recommend these values, and this is exactly what we find. Of course, then you measure this. Here they're recommended, but you don't have if it is loose sand. But we know that for loose sand, we found values like this and this, etc. And these tables, in my opinion, are important because are distillation of case histories, because moduli by manuals are simply normalized case histories, because they tell the values that if you use the theory of elasticity, give the right settlement predictions. So this is the experience accumulated in case histories, and it has been found that if you use theory of elasticity plus this moduli, they will give the proper answer. So the agreement between MDMT and the value recommended, we think, is quite important to give us confidence on the moduli by DMT. This is a very nice picture that probably Paul may recognize. Is one number is enough? Because he in 2001 said, we measure SPT, and then we want from this to obtain the shear strength. If we want to obtain modulus and skin friction, etc. So one number is not very much, of course. Actually, we should have 36 numbers, because if you have a stress which has 6 components and strain which has 6 components, 6 by 6 matrix of 36 parameters, which are variable as you load. But 36 is not so easy, but one maybe is too little. DMT is a 2-parameter test, and permits some elementary form of combination in which you get MDMT as I said before, correcting ED obtained by theory of elasticity, correcting by soil type, and KD. And here, this line emphasizes that one of them is stress history. And as was mentioned by Yemelkowski in one of the penetration conference 88, he said without stress history, it is impossible to select a reliable modulus, E or M, from QC. So stress history is fundamental. And also Leonard's calculating settlements on granular soils based on correlation, penetration resistance, soil modulus will seriously overestimate settlements if deposit has been pre-stressed. So pre-stressing is something that has a fundamental role in reducing settlements. Therefore, must be play some role when you calculate settlements, when you predict settlements. So having a modulus which incorporates the effect of stress history is in the right direction. We have seen many times this picture, but reminds this is now more than 30 years old. These photographs were done by Balig and Scott, and were in the clay, in the real thing. They are not numerical models. This is the real clay, and we have both cases. We have distortions, but you see that here we have something like a clay juice in the place where you usually put the porous stone for dissipations. And we know what the soil does when you make clay juice. Well, this is a classic, a particular case of the Lida clay, but you know that the Lida clay, you can put a lot of weight on it, but if you make something like this, then you can put in a glass. So this is okay for rupture, but when you're looking for deformation or stiffness, perhaps you are in a better condition if you are loading a bulb of soil here, which is distorted, but not in a way comparable with this one. And this is a picture that was also by Paul Main. He tells me that he tells to his student that insists with his students that of course deformability or stiffness and strength are not the same thing, are two different properties. You can have in the stress strain curve the same strength, but you can have a different slope for reaching that strength. On the other hand, this is like steel. All steels have more or less the same modulus, but the strength can be much more different. So these are two different properties. So strength is one thing, deformation is another thing. Another thing I want to clarify, maybe not here in this audience, but sometimes many people confuse the MT with the pressure meter. So I think there are considerable difference. I like penetration testing for reasons I already mentioned. The operator cannot make damage because you have to make PMT in a pre-drilled, calibrated, this is a terrible word, in a calibrated hole. Now, if you are in clay, you may have a calibrated hole. What is a calibrated hole? If you are in sand or with water, etc. So the big difference is that the operator can do damage. Not only the operator, maybe the soil itself does not permit to have a very good hole. And another point is what you do as a first action in a pressure meter, you destroy the horizontal stresses, because when you make a hole, the horizontal stress are reduced to 0, which is a trivial number that you cannot use. When you penetrate with the MT, you increase the pre-existing horizontal stress, but at least you can make a correlation because you have something which is not trivial. So you can go from KD to K0 and these kind of things. And also what, again, this is my personal opinion, so could be completely wrong. With PMT, I'm not very familiar, but I know that there are a multiplicity of methods for correcting for disturbance. So each one can interpret in a different way when the curve, how to correct the curve. I remember one time Ortigao, the Brazilian friend, told me, oh, we got the very similar prediction provided we use a special correction in the curve fitting applied to pressure meter. So if you had to use a special correction and maybe another engineer uses a different correction, this of course can be confusing. So DMT is not in the category of instrument using a hole. It avoids a hole. Is a penetration testing that can also have a dilatation. As we know, because we are discussing this, the flat dilatometer has a flat shape. Most of the other tools are cylindrical. So there are some background information that should be known by everybody. When you have a cylindrical tool, behind the tip there is the formation of enormous, the formation of a ring, highly pre-stressed because the soil is strongly pushed, and then after the shoulder there is a reduction of this high stress, but there is it remains in place a ring, a parasitic ring that make blind the sleeve. So the horizontal stress against the sleeve finds this obstacle and cannot go to make sensitive the sleeve to the horizontal stresses. So this phenomenon makes difficult to have the sleeve sensitive to horizontal stress in situ. And in fact, in one of the paper by Huang, which is also in this room, he concluded that sigma H sleeve is insensitive to sigma H in situ and highly variable because the decay from this high value to a lower value is very ill-conditioned, quite variable. I think with all cylindrical problems, you have this problem. And again, though I'm not familiar, I think the cone pressure meter, one of the reasons why did not go very fast is in this zone you are behind this parasitic ring. But of course, we don't want to go into this. I just want to conclude here that a flat shape implies much less arching because the shape, the cross shape of the DMT is about 1 to 7. And for instance, would you ever make a tunnel with the shape 1 to 7 vertical to horizontal? Never, because you would not have arching. So you try to have it circular or elliptical, but never of this shape. So we think it is reasonable to assume that with the flat shape, you avoid the problem of arching that we have just seen. Often DMT has been used for before, after. DMT before after is used to control compaction because of course when you compact you increase the modulus. DMT has been found to be more sensitive to compaction than other tests because many researchers have observed that they find that when you compact both you have an increase both of QC and DMT, but DMT increases at a faster rate. So if this is the increase in QC is 10%, you find that DMT increases 20%. Schmertmann found this in 1986. There is a paper from him, important paper, dynamic compaction of a sand site, and found that the increase in M was about twice the increase in QC. These people in Scandinavia found a similar result. This found similar results, and the Ghent group also studying the effect of the installation of Atlas pile noted that DMTs before-after installation demonstrate more clearly than CPT beneficial effects of the Atlas installation. So we think, as Roger said before, that it is important that DMT is more sensitive to even delicate effects in the soil. Well, this more or less repeats the previous slide. Shows that when you compact, before compaction, you have a QC and MDMT, let's say. When after compaction, both increase, but QC increases a little, MDMT increases a lot. And the ratio of this to this and this to this also increases, because before compaction, when the soil is nearly normally consolidated, you have a ratio 5, 6, 7. After compaction, when you have imparted stress history to your soil, this can be 20, 25. Using DMT for compaction can have some advantages, because since QC is scarcely sensitive to sigma H, QC reflects only part of the benefit, does not reflect the increase in delta sigma H. And according to Massage, the settlement predicted by QC after compaction can be too big. The consequence is we compact more than necessary. If we use MDMT to control compaction, since the MDMT incorporates sigma H, the benefit, the settlement predictions incorporate the benefit of increased sigma H. And in this case, we could possibly avoid waste. In other words, if we by DMT, it seems that we can feel many advantages reducing sigma H. So is a more direct link to the settlements. And I think also very appropriate observation by Schmertmann in '86 was that since the scope of why do we compact? We compact to limit the settlements. So it is more rational to write a specification in terms of modulus rather than DR. What has the DR to do with our scope? The real scope is to limit settlements. If you want settlements, go directly to settlements, not to relative density, to go to modulus directly, rather than pass through relative density. We have seen in 2 slides ago that the ratio MDMT over QC during compaction increases from 5 to 10, let's say, to 25 to 30. Now, during compaction of a loose sand fill, we have already seen that this ratio alpha increases, but the compaction means imparting OCR and stress history. So alpha, this ratio is usable as an indicator, approximate indicator of OCR. This could be one of the few ways to estimate OCR in sand, because when we find the value of alpha 5 to 10, this means normally consolidated sand. When it's in the other range, it means over-consolidated sand. And of course, from OCR, we can also have an indication of K0 in sand. De Vincenzi in Spain found that the reverse is true. He had a loess which had a stress history due to cementation, really. And the wetting, this loess reduced the stress history, the structured. So alpha went from about 20 before wetting to 8 after wetting. The next 2 slides that I will not show, but will be shown by Monaco, are actually taken from 2 slides shown by the Yamorkowski research group in the Atlanta conference in '98. and in which they show essentially that if you, in the calibration chamber, pre-strain the sand, then KD increases much faster than penetration resistance. And pre-straining is an effect not easy to detect by other methods. It's like aging, more or less. It's a tenuous form of aging. So the next two slides, since they are relevant to liquefaction, which will be discussed by Monaco, now I'm not going to talk about them. I just announced that DMT can fill, KD can fill quite well this aging manipulation. This is about slopes, and this also will be dealt by Monaco. Coefficient of consolidation permeability from T-flex. Here, the idea is to get the coefficient of consolidation and the coefficient of permeability from it using the decay curve. So this test consists in stopping the penetration at the given depth. So you stop the blade at the depth. You start the stopwatch at that time. The 0 is when you go at that time, that depth. And you monitor the total contact stress decay. And of course, in soils which are fast to consolidate, this curve is very inclined. The slope is very fast anyway. In clays which are highly permeable, this curve is much more horizontal, let's say. And we used as a marker point the T-flex. Since we don't monitor U0, we cannot use T50 when the dissipation is 50% of the delta U, etc., etc. So we had to find a different marker point, which incidentally has been suggested for the odometer too, so it's not a new idea. Anyway, what you get from this type of curves is the T-flex, and then you put T-flex in the formula below, and you get CH. This number 7 was obtained again as a number connecting theory, because the theory is missing to what you want. Because the theory actually exists, for instance, for the pressure meter, the holding test. You know the holding test, and Anderson developed the theory for the total stress decay. But DMT is not circular, so could be elliptical, maybe the theory. So the theory is not available, but a number exists. So if when the theory will be available, perhaps here we shall have a different number. But the two things are anyway connected. In conclusion, this is another application in which when you make a dissipation test, you can get CH and K. I must say, however, that this test takes longer than with the CPTU. So it's rather expensive because nobody wants to stop just to make a test like this. So unless you really have a good reason to do it, we think this is quite accurate, but can take 1, 2, 3 hours. Whereas with the cone you can do frequently in much less time. So from the viewpoint of the time, this is something that we try to avoid. But in many cases in which you need the accurate values, we use it. Just a few words to inform that in this 90-kilometer road in Bangladesh, we used the DMT as an alternative way to check the compaction that was initially specified in terms of CBR, Proctor, E-plate. So as an alternative to the initial specification, it was developed an acceptance MDT profile, and was used as an economical production method for quality control of compaction with only occasional verifications. But apart from this, I found very interesting the shape of the profile of M that we found below in the compacted soil. Almost invariably in 60 profiles we made, always the maximum was at about 25, 26 centimeter, the maximum. But this is reasonable because here the high horizontal stresses cannot be sustained by the soil. So there is it's intuitive that there must be a maximum at some depth. But this is very nice shape because when you make E-plate by the plate of the plate loading, you just get one, let's say, modulus, but it's an integral modulus. In this way, you have a profile of the modulus with depth. And also some colleagues which are expert in payment design say the tendency is to calculate today payments using moduli rather than using tests like CBR. So maybe this is what is something that they have to tell us. Anyway, by this way, we can provide them some kind of modulus with depth. How to use DMT for finite element input analysis? Of course, the easiest way is to use the modulus, MDMT or Young's modulus, plus linear elasticity. Many people use this, and that's it. There are many other things that can be said, but Monaco will cover this topic for Plaxis parameters. So I don't think we want to talk about this. Remaining in finite element application, many of them, these methods, require the G-gamma degradation curves. Many people in this planet are looking for this G-gamma degradation curve. And typically, when this curve is needed, one what does the cross-hole test, downhole test, and gets G0. Then the problem, of course, is how to guess the decay, because there are various types of decay. Some decay very soon, some do not decay soon. So if we have just 1 point, 1 point is not sufficient, because then we have to choose one of these curves. And maybe DMT can help, because since we have a modulus, we could have a second point, and then which cannot, I would like to have 10 points, but 2 points is much more than 1 point. And we can have a second point provided we know to which range this M corresponds. And we have analyzed the case histories where DMT predicted well the settlements, and we found that in the zones where most of the settlements occurred, we found this value 0.05 to 0.1% for the second point, which is this bar here. So this is an approximate tentative way of finding the second point, of locating the second point in the curve, so you can then choose better the decay curve. Even other researchers have given some idea of the shear strain they think can be associated with DMT, and one of these people was Main. He gave essentially the same range, a value in the range that I indicated before, and also Ishihara, here you cannot read, but anyway, he mentioned a similar shear strain. Of course, I don't think these things come from measurement or any specific research, but anyway, is their broad idea of where you could be, and it is good to see that it corresponds to the values indicated in the previous slide. Here we have many researchers, as you can see here, have tried to correlate ED, G0 to ED, probably because these are efforts to predict G0 from ED. And they found some correlations, but of course today, since we have also G0, it's better to measure both. So this was the stimulus to SDMT, to obtain G0 rather than by correlations with ED, to measure directly also G0. This is a historical picture by Main and Martin in '98, in which they showed the initial seismic flat dilatometer test in their clays. At the time, they were a little too far from the rods, but anyway, they had this idea, because the idea was to have at the same time G0 and to have operative modulus. Here we, this slide, the top more or less repeat what we have said. Since the operative range is here, if we are from G0, and this is the decay curve, it is difficult to go from G to the operative range, because what we have to do to use, let's say with theory of elasticity, we measure G0 and then you have to divide by 2, by 5. And then if you are here at a very high strain, like you see, what you do, you multiply by 2, by 20. So it is good to be in the operative range already, because from what I said, there is reason to presume that M is here already. So you don't have to go to M from G0 or to go to M from here. You if you have MDMT, you are already in the operative zone. And this is an important result shown by Yamashita, Yamalkowski, Lopresti, in which basically what they did was take a group of normally consolidated specimen, then a group of the same specimen but over-consolidated. And then they measured the variation of the modulus in the normally consolidated group and the under-consolidated group with strain. And they found that at the very low strain was not important if it was NC or OC, because the ratio was about 1. In the operative range, there was a big difference in behavior because the modulus was much higher for the over-consolidated specimen. And then when you are at high strain, again, the over-consolidation is not important. So what we learn from this picture, which is maybe not so easy to understand in a few seconds, is that OCR does not affect G at very low or at very high gamma. So OCR affects the modulus, especially at operative strains. So it is important, for instance, for settlements. We know that OCR is important, as Kempton explained us very well, and many, many others, that over-consolidation is an important fact at operative strain. But when you are very low or very high, OCR is not important for the modulus. And this helps to explain why G0 and QC do not reflect OCR, and confirms the notion that OCR is very important for settlement, and that you cannot predict settlements by parameters scarcely influenced by OCR. This is the same picture, not very good, but in the original paper by Yamashita, Yamalkowski, Lopresti. I think this picture, which goes back to Bishop 50 years ago, has something to do with the Yamashita, Lopresti, Yamalkowski paper, because after all, maybe I still have to think about that, because they showed at the time that changes in U and the A parameter during application that deviate to stress. And they found that at the low strain, they behave in the same way. Delta U here and here is the same, and A is 1/3, like the theory of elasticity for both. So at the very low strain, really normally consolidated and over-consolidated behave in the same way. This we all know this picture from the Bible of the triaxial test Bishop. So only at when the strain becomes significant, then dilatancy can show up if it exists, and then there is the difference between the two. So I think this this very old picture, after all, has something to do with previous research, and all of them, of course, reinforce each other. In conclusion, we think that the best applications of DMT are the MSU profile, the most useful, estimating settlement deformation, monitoring soil improvement, recognizing soil type, verify if slopes contains active old slip surfaces, useful information also on OCR and K-knot in clay, coefficient of consolidation permeability, PY curves for laterally loaded piles. This will be presented by Monaco. Sand liquefiability. We have something to tell you about this. Friction angle in sand, which is not the best thing that DMT does. It gives, we think, 2, 3, 4 degrees too conservative friction angle, but better than nothing in many cases. Some information of OCR and K-knot in sand in the way I said before, and I think it's the last one. So if the purpose is to profile hard soft layers, SPT, CPT may be preferable because they cost considerably less, but depends on the accuracy that you need. In many cases, you just want to know if the settlement is 1 centimeter or 10 centimeter. In this case, you can stay well with SPT, CPT. If you want more accurate settlements, then use DMT. So the last two lines are that use DMT when settlements are important, if you have strict specification, for instance, by railway, or if you need to decide piles or shallow foundations. I know that Roger is very sensitive to this matter because he very frequently says that he has been able to replace initially intended pile foundations with shallow footings with considerable savings. So in general, we think that DMT can be usable conveniently when the formation parameters are important. I think this was the last one. Yes, thank you for your attention.
Good morning, ladies and gentlemen. My name is Paola Monaco. I'm from the same university in Italy of Silvano Marchetti. So my boss asked me to present some of the DMT applications in this short course. And the topics I will talk about are the use of DMT for design of laterally loaded piles and for design of multi-anchored diaphragm walls. Then I will talk about the use of DMT for evaluating stability of slopes. And then after the break and after other presentations, I will talk about the use of the DMT for evaluating the liquefaction potential of sands. Okay. So let's start with the first topic is the use of DMT for design of laterally loaded piles. In particular for deriving PY curves for design of laterally loaded piles. I've seen there are also some contributions on this topic in this conference. So it may be appropriate to recall that the initial original stimulus that has led to the development of the DMT was just to obtain a tool for deriving parameters for design of laterally loaded piles. The picture in the slide is taken from the note by Marchetti in 77 at the Tokyo conference. and shows the various configurations that have led to the final configuration of the DMT. And there are some similarities between the DMT and laterally loaded piles. Both are structural elements installed in the soil, and both are then subject to lateral deformation. In view of these similarities, the DMT appears particularly fitting for deriving parameters for design of laterally loaded piles. This slide summarizes the two methods that we currently recommend for deriving PY curves for design of laterally loaded piles from DMT. The first one was introduced by Robertson and colleagues in '87 and applies both to clays and sands. And substantially, the method by Robertson is an adaptation of early methods for deriving PY curves from laboratory soil properties based on the traditional cubic parapole approach by Matlock 70. And in the adaptation by Robertson, these laboratory soil properties are derived from DMT by use of a series of correlations. The second method mentioned here, the references are indicated in the bottom of the slide, was developed by our group for clays, and is a more straightforward procedure for deriving PY curves directly from DMT results, bypassing the correlation chain involved by the Robertson method for deriving laboratory soil properties from DMT. So this is incidentally one of the few direct methods for design which make use directly of DMT results, avoiding intermediate parameters. Both methods apply for the case of single pile and for first-time monotonic loading. I won't give many details about the method, just to recall the basic equation of the PY curve used by our method. In this case, the PY curve at each given depth is described by a hyperbolic tangent function, which is written in the figure. And so this curve is completely defined by two parameters, PU, which is the ultimate lateral soil resistance, and ESI, which is the initial tangent soil modulus. These two values are derived directly from DMT results and completely describe the curve at each depth. The equations are written in the slide, the formula. And K1 and K2 are two empirical coefficients that were derived from field test results from lateral load tests on full-scale piles in normally consolidated clay site in Italy. And it should be noted that the ultimate lateral soil resistance is strictly related to shear strength of the clay, because it is a function of P0 minus 10, that is the same expression that we use to derive the undrained shear strength of the soil, of the clay. While the initial tangent soil modulus is strictly related to stiffness, because it's derived simply from the dilatometer modulus ED. So in this way, we think that we have found the best match between corresponding parameters representing shear strain failure and stiffness in the initial part of the curves. Both methods that I have mentioned by Robertson and our method have been validated on full-scale load tests on piles at various sites. The example shown in this figure was the comparison of horizontal displacement with depth measured by inclinometers and predicted by both the methods, by Robertson and ours, in lateral load tests on full-scale piles in this normally consolidated soft clay in Italy. And it can be seen that the agreement between measurements and the predictions by both methods is quite good. And it was found in general that both methods give similar predictions, and these predictions are generally in very good agreement with the observed behavior. Similar information have been given also by other groups like NGI and Georgia Tech. Some information on the use of DMT data to for design of laterally loaded pile groups can be found in this paper by West and Townshend, where PY curves were derived from DMT and pressure meter based on a large-scale load tests on groups of 16 piles. So who is interested in this topic can refer to this paper. So I will now talk about the use of the DMT for design of multi-anchored diaphragm walls, in particular for the evaluation of the coefficient of subgrade reaction to use with a spring model for calculations. This kind of structure, multi-anchored or multi-propped diaphragm walls, are widely used today for retaining deep open pit excavation, like, for example, car parkings in urban environment, and often are used in combination with the top-down construction technique. Therefore, to calculate the structure, it is necessary to use methods so we take into account the interaction between soil and structure. And this method can be the finite element methods, or the old spring method, which is still in Italy, is still widely used for doing a calculation of diaphragm walls. And this method, the spring method, of course, is simple to use but have several drawbacks. And the most crucial step is to apply this method is the selection of the coefficient of subgrade reaction on a rational way. And this is very important because this coefficient is the only parameter defining the interaction between soil and structure with this model. This parameter is something strange, really. It's a hybrid parameter because it depends on soil modulus, but it also depends on a number of geometrical mechanical factors whose meaning is not well understood, really. In any case, engineers are familiar with moduli, with soil stiffness, and not with this strange coefficient of subgrade reaction. Therefore, even crude relations for deriving this coefficient from usual soil stiffness parameters like the constrained modulus may be useful to engineers. Most of the existing formulations for deriving this coefficient of subgrade reaction for diaphragm walls have a formulation of this type, where the coefficient of subgrade reaction is directly proportional to soil stiffness and inversely proportional to this that we have called B, that is a sort of characteristic dimension representing the width of the soil zone loaded by the diaphragm walls. It should be noted that most of the indications available in literature, for examples in these references, for calculating these characteristic dimensions generally refer to cantilever walls. In many cases, this width B is equal or proportional to the free height of the wall or to the embedded depth of the cantilever wall. The estimate of this dimension B in the case of multi-restrained walls is much more uncertain. because the earth pressure distribution may be significantly different from the one in the case of the cantilever walls. And many times it is much close to the K-node distribution. And this is due to the fact that displacements are limited by restraint. So I will talk now about some results that we obtained in a study that was presented in a paper at the Porto conference 2 years ago, where we tried to derive a tentative correlation between the coefficient of subgrade reaction for diaphragm walls and the constrained modulus MDMT. This slide summarizes the procedure that we follow to derive this relation. First, we made finite element analysis using Plaxis with soil input moduli estimated from MDMT, considering various combinations of wall soil stiffness, excavation depth, and prop spacing. Then we repeated the calculation by the spring model by varying the coefficient of subgrade reaction until the bending moments and the horizontal displacements of the wall were nearly equal to values calculated by Plaxis. In this way, we could derive best fit values of the coefficient of subgrade reaction, those giving the best match with the Plaxis results. And we try to establish this tentative correlation between KH and MDMT. Of course, this study has some limits. In this case, the values of the coefficient of subgrade reaction were really calibrated based on finite element results that were assumed as being the reality in this case. The study was purely numerical without comparisons of predictions with observed behavior in real cases. Therefore, it needs a strong validation. I don't want to give many details about the calculation in this study. Who is interested can refer to the paper, but I just want to mention this. That could be an interesting point for the Plaxis users, how to select Plaxis stiffness input parameters starting from the DMT moduli. In this study, we made use of the hardening soil model incorporated in Plaxis. And this model requires the definition of 3 moduli at the reference pressure of 100 kilopascal, and a one-dimensional tangent modulus, a triaxial modulus E50, and an unloading-reloading modulus. And these moduli are related to current stress according to these expressions, where the exponent of the relation is usually varying in the range 0.5 to 1. C'era un altro? Okay. There was this study by Chance and Vermeer who made a literary survey on wide range of remolded quartz sands from very loose to very dense, and they found that the values of the E50 triaxial modulus varying in the range 15 to 75 megapascal, that was found very close to values of MDMT found for sands of similar densities. And also in this study and in this other study, which is mentioned here by Vermeer, it is stated that the triaxial modulus can be correlated to the 1D modulus, to the odometer modulus, and substantially triaxial can be estimated from odometer modulus. So in this case, in this study, all the moduli required by the hardening soil model in Plaxis were estimated starting from one modulus, that is MDMT, assumed as an operative modulus. these relations were used. The Dilatometer modulus, which is the corresponding of MDMT, was assumed equal to MDMT at the same stress. The triaxial modulus was assumed equal to the Dilatometer modulus, and the unloading reloading modulus was assumed equal to 4 times the Dilatometer modulus, following the indications given in this reference. So the calculations was done, it was a parametric study, so it was done for a number of combinations. 3 soils were considered, soft soil, a medium soil, and a stiff soil, having different values of reference moduli. And the only difference between the 3 soils considered concerns stiffness. All the other parameters of representing shear strength were considered the same for all the 3 cases. But in all the 3 cases, the ratio between these 3 moduli required by the hardening soil model was 1:1:4, as I explained before. And so this is just to recall some data for which the calculation was made, because we will see that we can use maybe some results of this study for similar conditions. So we analyzed the 3 different cases of excavation depth varying from 12 to 24 meters, 2 values of prop spacing, 3 and 6 meter, and a fixed embedded depth. We also considered 2 different, extremely different values of soil stiffness, a rigid wall having a flexural stiffness corresponding to a 1 meter thick concrete wall, frequent situation. And another case is a flexible wall having the stiffness corresponding to typical steel sheet pile wall. And we considered the construction sequence according to the top-down technique. So the first step is always prop installation, followed by an excavation down to the next prop level, and so on until the final excavation depth. And this technique involves a high degree of restraint of the structure. And this is an example of the comparisons of the results that we obtained. This case refers to the combination soft soil flexible wall to an excavation depth of 18 meters and a prop spacing of 3 meters. We have compared the results obtained by Plaxis and by the spring model. In this case, as I said before, the calculations by springs were repeated until we had the best match with the Plaxis result. In this case, we can see that the matching, both in terms of displacement and in terms of bending moments, are very good. So we could derive the values of the best fit coefficient of subgrade reaction. Of course, these values was varying for different cases considered in this study. Next. So we try to examine the variation of this best fit coefficient of subgrade reaction as a function of the excavation depth, as shown in this figure, which refers to the case of the 1 meter concrete diaphragm walls, so a stiff wall. And these curves represent, these families of curves represent the 3 types of soil, and the 2 values of prop spacing considered. It can be seen that the coefficient of subgrade reaction reduces as the excavation depth increases, but after a certain excavation depth, it seems to remain nearly constant. And also, considering the same soil and the same depth, we see that this coefficient of subgrade reaction reduces as the prop spacing increases. That is, the wall is less restrained. And also there is a variation depending on different stiffness of the soil. So what we found, was expectable is that this coefficient of subgrade reaction decreases when wall deformations increase due to an increase of the excavation depth or to decrease in restraint degree. Therefore, this corresponds to an increase in B, that is this characteristic length, that is a width of soil zone involved by wall movements. We tried to represent this situation by this relation between the coefficient of subgrade reaction and the constrained modulus MDMT that is similar to existing formulations for the coefficient of subgrade reaction. We think that we can use this relation as a broad indication for selecting the sign values of B and so of the coefficient of subgrade reaction for the case of multi-proper diaphragm walls in cases that are similar for wall geometry and stiffness and prop spacing and for various ranges of soil stiffness to the cases that we have analyzed in this paper. And this relation has been expressed in the form of charts that are in the next slides. And from this figure, we can obtain the B value to introduce into this formula to derive the coefficient of subgrade reaction as a function of the excavation depth for two values, or in the middle between these values of prop spacing, and for different ranges of soil stiffness. So this is the case, all the cases shown are referred to a stiff diaphragm wall, and this is the case for a soft soil. Next. This is the same figure for the range of the intermediate stiff soil. And this is the same figure for the case of a very, very stiff soil. So we can use these charts as a broad indication for deriving the coefficient of subgrade reaction for similar cases.